Hello and welcome back. I'm glad you found your way here again tonight. Tonight, we're going to slow all the way down past the pace of rivers, past the pace of forests growing, down to the almost unimaginably slow rhythm of stone itself. Tonight's journey is through geology, the ancient, patient story written into every mountain, canyon, and grain of sand beneath your feet. If this is your first time here, consider subscribing to Drowsy with Facts, where every episode is 100 gentle facts, softly narrated, designed to carry you all the way to sleep. For now, let's begin. It helps to begin gently with the very ground you're resting on right now and the deep, slow structure that lies beneath it. Earth's solid outer shell, called the crust, is surprisingly thin compared to the planet as a whole. Beneath the oceans, it can be as little as 3 miles thick, while beneath the continents, it stretches to around 25 miles on average. Beneath that crust lies the mantle, a much thicker layer of hot, slowly flowing rock, extending nearly 1,800 miles down toward the planet's core. Although the mantle is technically solid, it behaves, over the scale of millions of years, almost like a very thick, very slow liquid, gradually churning and shifting in vast, patient currents that quietly shape the world above. This slow churning within the mantle drives one of geology's most fundamental processes, plate tectonics. Earth's crust isn't one continuous shell, but rather a patchwork of large, rigid plates floating atop the softer mantle beneath, drifting at speeds of roughly an inch or two per year, about the same rate your fingernails grow. It's a pace so slow that it's utterly imperceptible in a single human lifetime. And yet, given enough time, it's responsible for raising entire mountain ranges, opening vast ocean basins, and rearranging the layout of the continents themselves, again and again, over hundreds of millions of years. Mountains in particular offer some of the clearest evidence of this immense tectonic patience. The Himalayas, home to the tallest peaks on Earth, are still slowly rising today, a direct result of the Indian tectonic plate continuing to push into the Eurasian plate, a collision that began roughly 50 million years ago and continues almost imperceptibly even now. Remarkably, geologists have found fossilized marine creatures, including ancient seashells embedded in rock near the summit of Mount Everest, a quiet, stony reminder that the same rock once rested at the bottom of an ancient sea, long before it was slowly folded and lifted over tens of millions of years into the highest point on the planet. Rock itself, despite feeling so solid and unchanging in the moment, is constantly being formed, broken down, and reformed through an ongoing process geologists call the rock cycle. There are 3 broad categories of rock, each formed through a different, distinct process. Igneous rock forms when molten rock, called magma while underground, or lava once it reaches the surface, cools and hardens into solid stone. Sedimentary rock forms when small particles of sand, mud, and mineral fragments gradually accumulate in layers, often at the bottom of ancient seas or riverbeds, and are slowly compressed and cemented together over vast stretches of time. And metamorphic rock forms when existing rock, whether igneous or sedimentary, is subjected to intense heat and pressure deep underground, transforming its internal structure into something new without ever fully melting. These 3 rock types are locked in a slow, continuous cycle with one another, each one capable, given enough time and the right conditions of transforming into either of the other two. A sedimentary rock, buried deep enough and subjected to enough pressure, can gradually become a metamorphic rock. That same metamorphic rock, if it happens to melt entirely deep within the crust and later cools again, becomes an igneous rock. And an igneous rock, slowly worn down by wind and water at the surface, breaks apart into the very sediment that will one day compress into new sedimentary layers. It's a quiet, endless loop, unfolding over timescales so vast that no single rock and no single human lifetime ever witnesses the full journey from start to finish. Sedimentary rock, in particular, offers geologists one of their most valuable tools for reading Earth's deep past, thanks to a principle sometimes called the law of superposition. In an undisturbed sequence of sedimentary layers, the oldest layers naturally rest at the bottom, with progressively younger layers stacked above them, since each new layer of sediment settles on top of whatever came before it. This is part of why the layered, banded walls of a canyon can feel almost like reading a book. Each colorful stripe of rock represents a distinct period of time, sometimes spanning thousands or even millions of years, quietly stacked one atop another in careful, chronological order. There may be no better example of this principle than the Grand Canyon, carved by the Colorado River over roughly 5 to 6 million years. The canyon's exposed rock layers reveal an extraordinary span of geological time, with the oldest rocks near the bottom of the canyon dating back nearly 2 billion years, while the youngest layers near the rim are a comparatively recent 230 million years old. Standing at the canyon's edge and looking down, a visitor is, in a very real sense, looking backward through almost half of Earth's entire history, layer by layer, all the way down to rock that formed long before complex life had even begun to emerge. Rivers like the Colorado are remarkably effective sculptors of the landscape, and their patient, persistent work is worth pausing on for a moment. A river carves through solid rock, not through any single dramatic event, but through countless small abrasive collisions as sand, gravel, and rock fragments, carried within the flowing water, grind steadily against the riverbed and canyon walls, a process geologists call erosion. Combined with the slow, steady uplift of the surrounding land through tectonic forces, a river can, given enough time, cut down through thousands of feet of solid rock, one microscopic scrape at a time, until it produces something as vast and dramatic as a mile-deep canyon. Water shapes the landscape in quieter, less obvious ways as well, particularly underground, where it plays a central role in forming caves. Many caves develop when slightly acidic groundwater, formed as rainwater absorbs small amounts of carbon dioxide from the soil, slowly dissolves certain types of rock, particularly limestone, over thousands or even millions of years. As this slightly acidic water percolates through cracks and fissures, it gradually widens them into larger and larger passages, eventually forming the sprawling underground chambers found in cave systems around the world. Within these caves, water continues its slow work, even after the main passages have formed, mineral-rich droplets slowly depositing tiny amounts of calcium carbonate as they drip from the ceiling, gradually building the icicle-like formations known as stalactites, which grow downward from above, and stalagmites, which rise upward from the cave floor below, some growing at a rate of less than a single inch every 100 years, Crystals, too, tell their own quiet story about the conditions in which they formed, and their structure offers a remarkable window into the patient, orderly nature of geological time. A crystal forms when atoms or molecules arrange themselves into a highly ordered, repeating pattern, and the size of the resulting crystal often depends directly on how slowly that arrangement was allowed to take place. Magma that cools very slowly deep underground, sometimes over many thousands of years, allows individual crystals ample time to grow large, sometimes to remarkable sizes, while magma that cools rapidly at the surface, as lava exposed to open air, produces rock made of crystals far too small to see with the naked eye, or, in some cases, rock with barely any crystalline structure at all, as is the case with volcanic glass known as obsidian. Some of the largest crystals ever discovered were found in a cave in Nica, Mexico, deep beneath a working mine, where geologists encountered a chamber filled with massive, translucent selenite crystals, some reaching nearly 40 feet in length. These extraordinary formations grew over hundreds of thousands of years within a cave that remained naturally filled with mineral-rich water at a remarkably stable, warm temperature, conditions patient and consistent enough to allow individual crystals to grow to a scale rarely seen anywhere else on Earth, hidden away in the dark, undisturbed for hundreds of millennia before miners first happened upon the chamber in the year 2000. Volcanoes represent one of geology's more dramatic and sudden processes, though even here, the underlying forces at work are the product of slow, patient buildup over long stretches of time. Volcanoes typically form at locations where magma from deep within the mantle finds a pathway toward the surface, often at the boundaries between tectonic plates, where one plate is being forced beneath another, or where plates are gradually pulling apart, allowing magma to rise and fill the resulting gap. Not all volcanoes behave the same way. Some, like the broad, gently sloping shield volcanoes found in places like Hawaii, tend to produce relatively slow, flowing eruptions of fluid lava, building up gradually over many eruptions into enormous, gently rounded mountains. Others, like the steep, cone-shaped stratovolcanoes found around the Pacific Ring of Fire, tend to build pressure over long periods before releasing it in far more explosive, sudden eruptions. Minerals, the individual chemical building blocks that make up rock, come in an extraordinary variety, with more than 5,000 distinct minerals currently recognized by geologists, each defined by its own unique chemical composition and crystal structure. Quartz, one of the most common minerals found in Earth's crust, appears in countless forms, from the clear, glassy crystals sometimes found in caves, to the fine, sandy grains that make up many of the world's beaches. Some minerals are prized for their rarity and beauty, eventually cut and polished into gemstones, while others, like the many varieties of clay and mica, remain quietly abundant and essential, forming the practical foundation for everything from ceramics to construction, largely unnoticed by most people, despite their constant presence in daily life. Fossils too fall within the broader story of geology, since they're preserved almost exclusively within sedimentary rock layers, offering a remarkable window into ancient life, alongside the ancient landscapes that once surrounded it. Fossilization is, in most cases, an exceptionally rare event, requiring a very particular sequence of fortunate circumstances. An organism must be buried relatively quickly after death, typically in fine sediment that limits decay and scavenging, and the resulting sediment must then remain undisturbed for enormous stretches of time as it gradually hardens into solid rock. Given how rare these precise conditions are, scientists estimate that only a tiny fraction of all organisms that have ever lived were ever fossilized at all, making every fossil discovery a small, quiet piece of an otherwise largely lost and silent history. Earth's geological history is divided by scientists into an enormous, carefully structured timeline stretching back across roughly 4.5 billion years, organized into a series of eons, eras, periods, and epochs, each marking a distinct chapter in the planet's long story. This full span of time is often called deep time, a term meant to capture just how vast and difficult to intuitively grasp Earth's true age really is. If the entire history of the planet were compressed into a single 24-hour day, all of recorded human history, every civilization, every written word, would occupy only the final few seconds before midnight. A small, fleeting flicker at the very end of an extraordinarily long and patient story. Layered within this deep timeline, certain rock formations preserve remarkably clear evidence of dramatic events in Earth's distant past. A thin, distinctive layer of clay found in rock formations around the world, rich in a rare metal called iridium, marks the boundary between the Cretaceous period and the one that followed it, roughly 66 million years ago, and is widely understood by geologists to be direct evidence of the massive asteroid impact believed to have contributed to the extinction of the dinosaurs. It's a quiet, thin line of dark clay, easy to overlook if you didn't know its significance, and yet it marks one of the most consequential single moments in the entire history of life on Earth, patiently preserved within the layered rock ever since. Let's drift now toward some of the more unusual and striking geological formations scattered across the planet, each one shaped by its own particular combination of time, pressure, and patient natural forces. In Northern Ireland, the Giant's Causeway consists of roughly 40,000 interlocking, mostly hexagonal basalt columns, formed when a massive ancient lava flow cooled and contracted in a remarkably uniform pattern, cracking into these strikingly geometric shapes as it slowly solidified millions of years ago. In the American Southwest, formations like the towering red sandstone spires of Monument Valley were carved not by any single dramatic event, but through millions of years of slow, steady wind and water erosion, gradually wearing away softer surrounding rock and leaving behind only the harder, more resistant stone standing tall against the open desert sky. Salt, too, plays a quietly significant role in shaping certain landscapes, particularly in regions where ancient seas once existed and later evaporated entirely, leaving behind thick, buried layers of salt deposits. Because salt is considerably less dense than the rock layers that typically settle above it over time, and because it can behave in a slow, almost fluid manner under enough pressure and heat, these buried salt layers sometimes slowly rise upward over millions of years, forming underground structures called salt domes, occasionally pushing surrounding rock layers upward and outward as they rise, subtly reshaping the landscape from far below the surface, entirely out of sight. Earthquakes, much like volcanoes, represent one of geology's more sudden and dramatic expressions of a much slower, more patient underlying process. Along fault lines, where two sections of Earth's crust meet and grind against one another, friction can cause the two sides to become temporarily locked in place, even as the broader tectonic forces driving them continue pushing steadily in opposite directions. Stress gradually builds up along this locked boundary, sometimes over decades or even centuries, until it finally exceeds the friction holding the fault in place, causing a sudden, rapid release of built-up energy as the two sides abruptly slip past one another, sending powerful vibrations felt as an earthquake rippling outward through the surrounding rock. Let's spend a little more time with the slow, quiet forces of weathering and erosion, since together they're responsible for shaping nearly every visible landscape feature on Earth, working so gradually that their effects are rarely noticed except across generations. Weathering refers to the slow breakdown of rock in place without the material actually being moved, and it happens through both mechanical and chemical processes working together. Mechanical weathering includes forces like water repeatedly freezing and expanding within tiny cracks in rock, gradually widening them over countless winters, a process particularly powerful in mountainous regions where temperatures swing above and below freezing on a regular basis. Chemical weathering, meanwhile, involves the slow dissolving or transformation of minerals within rock, often through exposure to slightly acidic rainwater, or the gradual oxidation of iron-bearing minerals, the same basic chemical process responsible for rust forming on exposed metal, quietly turning certain rock surfaces a distinctive reddish-brown color over time. Once rock has been broken down through weathering, erosion takes over, physically transporting the resulting fragments elsewhere, whether by flowing water, wind, gravity, or slowly moving ice. Glaciers in particular are remarkably powerful agents of erosion despite their famously slow pace of movement. As a glacier slowly flows downhill under its own immense weight, sometimes advancing only a few inches or feet per day, it drags embedded rock and debris along its base, gradually grinding and scouring the landscape beneath it, carving out distinctive U-shaped valleys, quite different from the narrower V-shaped valleys typically carved by rivers. Many of the world's most dramatic mountain landscapes, including much of the Alps and significant portions of North America's mountain ranges, were substantially shaped by glacial erosion during past ice ages, when glaciers covered far more of the planet's surface than they do today. Deserts, too, showcase some of geology's more striking, wind-driven formations, since in these dry, sparsely vegetated environments, wind becomes an unusually dominant force in shaping the landscape. Wind-blown sand can, over long periods, gradually sculpt solid rock into dramatic, sometimes unusual shapes, wearing away softer layers of stone while leaving harder layers more intact, occasionally producing narrow elevated formations that appear to defy gravity, along with the more famous rolling sand dunes found in many of the world's great deserts. These dunes themselves are far from static, constantly shifting and migrating gradually across the landscape as wind continues redistributing individual grains of sand, sometimes moving an entire dune's position by dozens of feet over the course of a single year. It's worth pausing, too, on the remarkable diversity found among Earth's mountain ranges, since mountains form through several genuinely distinct geological processes, rather than any single universal method. Fold mountains, like the Himalayas we discussed earlier, form when two tectonic plates collide directly, compressing and folding rock layers upward much like a rug, bunching up when pushed from either end. Fault block mountains, by contrast, form when large sections of crust fracture along fault lines and are pushed upward or dropped downward relative to their surroundings, creating dramatic, steep-sided ranges like the Sierra Nevada in North America. And volcanic mountains, naturally enough, form through the gradual accumulation of erupted material over repeated eruptions, building upward one lava flow or ash deposit at a time until a substantial peak eventually emerges. Beneath the ocean's surface, geology continues its quiet work, largely out of sight, shaping a landscape every bit as dramatic and varied as anything found on dry land. Long, continuous mountain ranges called mid-ocean ridges wind their way across the ocean floor, marking the boundaries where tectonic plates are slowly pulling apart, allowing fresh magma to rise up and cool into new oceanic crust in a continuous, ongoing process. Along these ridges, the ocean floor is quite literally being created anew, spreading outward gradually in both directions at rates typically measured in just a few inches per year. A slow but steady process that has, over hundreds of millions of years, been responsible for opening entire ocean basins from what were once much narrower, more modest bodies of water. Gemstones among the most prized products of geological processes, each carry their own particular story of formation deep within the earth. Diamonds, the hardest naturally occurring material known, form under conditions of extreme heat and pressure, found only very deep within the mantle, typically more than 90 miles below the surface, before being carried upward toward the surface through rare, violent volcanic eruptions that occur far more explosively and far more rapidly than typical volcanic activity, transporting these deep-formed crystals upward in a matter of hours rather than the more typical slow crawl of magma toward the surface. Emeralds, by contrast, form much closer to the surface when the element beryllium happens to come into contact with chromium or vanadium under just the right conditions, producing the distinctive, vivid green coloration that has made emeralds prized across countless cultures throughout history. Opals form through an entirely different process altogether, as silica-rich water slowly seeps into cracks and cavities in rock, gradually depositing microscopic spheres of silica that, when arranged with sufficient regularity, diffract light in a way that produces the shifting, colorful play of light so characteristic of a fine opal. The boundaries where tectonic plates meet come in three broad varieties, each producing distinctly different geological features depending on how the plates are moving relative to one another. At convergent boundaries, plates move toward each other, either causing one plate to be forced beneath the other in a process called subduction, often producing volcanic mountain ranges and deep ocean trenches, or causing both plates to crumple and fold upward together if neither is willing to slide beneath the other, as is the case with the ongoing collision forming the Himalayas. At divergent boundaries, plates move apart from one another, allowing magma to rise and fill the resulting gap, a process responsible for the mid-ocean ridges we spoke of earlier, and also, on land, for the formation of continental rift valleys, like the East African Rift, where the African continent is slowly, almost imperceptibly, beginning to split apart into two separate landmasses. And at transformed boundaries, plates slide horizontally past one another without significant material being created or destroyed, a movement responsible for many of the world's most significant earthquake-prone regions, including California's famous San Andreas Fault. It's worth taking a little time to appreciate how relatively recently geology developed into the careful, systematic science it is today. For much of human history, the origin of mountains, canyons, and rock formations was explained primarily through religious or mythological frameworks, with little attempt at systematic, evidence-based investigation. It wasn't until the late 18th century that the Scottish geologist James Hutton proposed what became known as the principle of uniformitarianism, the foundational idea that the same slow, gradual geological processes observable today, like erosion and sedimentation, have been operating consistently throughout Earth's history, and that studying these present-day processes could therefore reveal the planet's deep past. Hutton's idea is controversial at the time, since they implied an Earth far older than most contemporary estimates allowed, were later expanded and popularized by the geologist Charles Lyell in the early 19th century, whose work profoundly influenced an entire generation of scientists, including a young naturalist named Charles Darwin, who carried Lyell's writings with him during his famous voyage aboard the HMS Beagle, and whose own later theories about the gradual pace of evolution owed a significant conceptual debt to the patient. Slow-moving processes Hutton and Lyell had first carefully documented in stone. Geothermal features, like hot springs and geysers, offer a particularly vivid reminder that Earth's deep, molten interior remains active even in places far removed from any obvious volcano. These features typically occur where groundwater comes into contact with unusually hot rock relatively close to the surface, often in regions where volcanic activity has occurred in the geologically recent past, even if no active volcano is currently visible above ground. A geyser forms when this heated groundwater becomes trapped within a narrow, constricted underground channel, allowing pressure to build steadily as the water is heated toward and beyond its boiling point, until the pressure finally releases in a sudden, dramatic eruption of steam and water, after which the cycle slowly begins building toward its next eruption all over again. Yellowstone National Park, sitting atop one of the largest active volcanic systems on Earth, is home to more geysers than anywhere else on the planet, including the famously predictable Old Faithful, which has been reliably erupting at fairly regular intervals for well over a century of careful observation. Mineral hardness, one of the fundamental properties geologists use to identify and classify different minerals, is measured using a simple, elegant system called the Mohs scale, developed in 1812 by the German mineralogist Friedrich Mohs. The scale ranks 10 common minerals from softest to hardest, with talc, soft enough to be scratched easily with a fingernail, sitting at the very bottom, and diamond, hard enough to scratch virtually anything else, sitting at the very top. Rather than measuring hardness through complex laboratory equipment, the Mohs scale works simply by testing which minerals can scratch which others, a delightfully straightforward method that remains widely used by geologists in the field today, more than 2 centuries after it was first devised, precisely because it requires nothing more than a small set of reference minerals and a keen, careful eye. Metamorphic rock, formed through intense heat and pressure without fully melting, comes in a remarkable variety of forms, depending on both the original parent rock and the specific conditions it experienced during transformation. Marble, prized for millennia as a sculpting and building material, forms when limestone, is subjected to heat and pressure, causing its mineral structure to recrystallize into the smooth, often veined stone, familiar from countless statues and buildings throughout history. Slate, valued for its tendency to split into thin, flat sheets, forms from the metamorphism of shale or mudstone under relatively moderate conditions, and gneiss, one of the more intensely transformed metamorphic rocks, often displays striking banded patterns of light and dark minerals formed when rock is subjected to such extreme heat and pressure that as minerals begin separating into distinct layers, a slow, patient rearrangement occurring entirely in the solid state, deep within the crust, over enormous stretches of geological time. The very idea of drifting continents, so fundamental to modern geology, was itself once considered a fringe, largely dismissed theory for several decades after it was first proposed. In 1912, the German scientist Alfred Wegener suggested that the continents had once been joined together in a single, vast landmass, which he called Pangaea, before gradually drifting apart into their current positions over millions of years. Wegener supported his theory with a range of evidence, including the strikingly puzzle piece fit between the coastlines of South America and Africa, along with the matching fossil species and rock formations found on continents now separated by entire oceans. Despite this evidence, most geologists at the time rejected Wegener's theory, largely because he couldn't adequately explain what mechanism could possibly be powerful enough to move entire continents. It wasn't until the 1960s, decades after Wegener's death, that the discovery of seafloor spreading along mid-ocean ridges finally provided the missing mechanism, and the broader theory of plate tectonics, building directly on Wegener's original insight, became firmly established as one of the foundational unifying principles of modern geology. In regions of the world with particularly cold climates, geology takes on a distinctive character shaped by ice in ways quite different from the glacial carving we discussed earlier. Permafrost, ground that remains frozen continuously for at least 2 consecutive years, underlies vast stretches of the Arctic and high-altitude regions, sometimes extending hundreds of feet deep into the earth. As this frozen ground repeatedly freezes and partially thaws across the seasons, it can produce distinctive surface patterns, including large, polygon-shaped cracks in the landscape, formed as ice wedges slowly develop and expand within the frozen soil over many repeated seasonal cycles, creating a strange, geometric patterning visible from above that looks almost deliberately designed despite being entirely the product of patient, repeated freezing and thawing. Elsewhere, in regions underlain by particularly soluble rock like limestone, a distinctive style of landscape known as karst topography can develop, characterized by sinkholes, underground drainage systems, and cave networks, all shaped by the same slow dissolving action of slightly acidic water we discussed earlier in relation to cave formation. Sinkholes form when underground cavities, gradually dissolved and enlarged over time, eventually become too large to support the weight of the ground above them, causing a sudden collapse that can range from a small, gradual depression to a dramatic, abrupt chasm opening within the span of just a few moments. An unsettling reminder that some geological processes, though built on centuries of slow underlying change, can conclude with startling suddenness at the surface. Occasionally, Earth's geological story is interrupted by forces arriving from well beyond the planet itself in the form of meteorite impacts. While most meteorites entering Earth's atmosphere burn up completely before ever reaching the ground, larger objects can survive the fiery passage through the atmosphere and strike the surface with tremendous force, leaving behind distinctive circular impact craters. Barringer Crater in Arizona, formed roughly 50,000 years ago by a meteorite measuring only about 150 feet across, remains remarkably well preserved today, nearly 3/4 of a mile wide, thanks to the dry desert climate that has limited the erosion typically responsible for gradually erasing older impact craters elsewhere around the world. Much larger impact structures, some spanning many miles across, have been identified throughout Earth's geological record, their outlines often only detectable today through subtle, carefully mapped variations in surrounding rock, having been worn down and reshaped by hundreds of millions of years of subsequent geological activity since the original impact occurred. Soil itself, so easy to overlook as simply dirt underfoot, represents one of geology's quieter, more essential achievements, formed through the slow, patient interaction of weathered rock, organic material, water and air, often over the course of many centuries. A single inch of fertile topsoil can take anywhere from several hundred to well over 1,000 years to naturally form, as rock is gradually broken down through the weathering, mixed with decomposing organic matter from plants and other organisms, and slowly organized by the activity of countless small creatures living within it, from earthworms to microscopic bacteria and fungi. This slow formation process stands in sharp contrast to how quickly soil can be lost through erosion, particularly when protective vegetation is removed. A reminder that this seemingly humble, easily overlooked layer represents a genuinely irreplaceable geological resource on any timescale meaningful to human civilization. Determining the actual age of rock rather than simply its relative position within a layered sequence became possible only with the development of a technique called radiometric dating in the early 20th century. This method relies on the predictable, steady decay of radioactive elements naturally present in small quantities within certain rocks and minerals. Elements that break down into different, stable elements at a fixed, well-understood rate, often described in terms of a half-life, the time required for half of a given radioactive sample to decay. By carefully measuring the ratio between the remaining radioactive element and the stable element it decays into, geologists can calculate with remarkable precision how long ago a particular rock originally formed. This technique has proven essential not only for dating rock formations directly, but also for calibrating and confirming the broader geological timeline, first established through the patient, careful, layer-by-layer observations of earlier generations of geologists, tying together centuries of careful fieldwork with the precise physical certainty of atomic decay. As we drift toward the end of tonight's journey, let's take one last slow pass back through everything we've traveled through together. We began deep beneath our feet with the thin, drifting plates of Earth's crust floating atop a slow, churning mantle, patiently reshaping mountains and oceans alike over hundreds of millions of years. We traced the endless quiet cycle connecting igneous, sedimentary, and metamorphic rock, and read the layered, stacked story of time preserved within canyon walls. each stripe of color marking its own distant chapter. We wandered through caves slowly dissolved and rebuilt by patient, mineral-laden water, and admired crystals grown large and clear over hundreds of thousands of years in warm, undisturbed dark. We considered volcanoes built from slow, accumulated pressure and fossils preserved only through rare, fortunate accidents of burial and time. We touched briefly the vast, almost incomprehensible scale of deep time itself, where all of human history amounts to only the final few seconds before midnight. And so tonight, we leave the story of stone exactly where it has always been. Patient, slow, and endlessly unfolding beneath our feet, quietly recording the passage of millions of years in layers of rock, crystal, and sediment, indifferent to the pace of any single human life, and yet somehow holding within its patient layers the entire deep history of the world we live on. There's something quietly comforting in that kind of patience, in knowing that the ground beneath you tonight has been settling, shifting, and slowly forming for billions of years, and will likely continue doing so, unhurried and unbothered, long after tonight has faded into memory. You've drifted tonight through rising mountains and carved canyons, through slow-growing crystals and patient underground rivers, through ancient seafloors lifted to mountain peaks, and the quiet, thin layer of clay marking the end of the dinosaurs. You've traveled further back in time tonight than any of us ever could in waking life, and you've done it without ever leaving the comfort of where you're resting right now. Let it hold you now, the same slow, patient stillness of stone, settling gently in the dark, asking nothing of you except to rest. Sleep well, and I'll see you next time for another 100 facts drifting softly into sleep.